week I said that I was going to talk about how like you go about making optimized signal templates using gradient descent and stuff, but I think now like this today would actually be better spent just talking more about how you actually implement a lot of this stuff in Arduino. And so I'll put off the gradient descent stuff until next week because, well, one of the reasons is that I couldn't get one of the, I couldn't get a complete example made in time of how you go about making one of the good templates in MATLAB and then also writing an Arduino program that does the correlation thing that loads the template from a file. So I should hopefully have that done next week. But for right now, I'm actually just going to go over some of the signal processing stuff that I brought up previously that we do on the Pied Piper project to make feature recognition a little easier. Okay, so this is the code that's just the stuff that I shared on Basecamp last week. So this is the correlation, just the simple template correlation thing. And just to be clear, were you able to get this working in the end?
Yeah, we got some examples working. I think we had a bit of an issue with what was it? One aspect of it, but I think we got it working in the end. Now we're working on implementing the FFT, so this should be a perfect topic for today.
Okay. So yeah, something I did that did get mentioned was the interrupt timer. Was that the thing you were having problems with?
Yeah, that's right.
Okay. So yeah, that I'm pretty sure I went over this a few weeks ago, but like the interrupt timer, unfortunately, it looks like for what you guys are trying to do, it's going to be kind of unavoidable just because if you need to, it sounds like the processing that you guys are doing can't have any blind time in it. So like what can happen, like if you didn't use an interrupt timer, what would happen is you would take forever doing each Fourier transform and not recording any new samples while you're doing that. And then you would have a bunch of blind time in between each Fourier window. And if you're trying to get really high temporal resolution on whatever your signal is, then then that would mess things up. So for what you guys are doing, I think you'll have to just deal with having an interrupt timer constantly doing stuff. But yeah, if this library, it should work. It should work fine on an ESP32, even if, so one of the things I'm going to be showing next is dealing with the interrupt timer when you're doing file IO and stuff, which is annoying. So are you guys doing any kind of off-chip communication while you are recording and sampling audio?
No, at least not yet. And I don't think that's part of the plans that we have so far. We're just going to wire a base shaker onto our board and have it go right between the two. Okay,
so yes, you shouldn't need to deal with like turning the interrupt timer off to do SPI and I2C communication or anything like that. Okay. So first of all, I'm just going to, yes, it's running. So I'm going to start off by pointing out something about this frequency correlation thing, which is that right now, this is set up. So the template in this example is initialized to just a bunch of ones or whatever the normalized. It's just a constant number across the whole template. And one of the consequences of that is that it correlates really, really well with random noise. So that's why when you first turn on the example, it hovers at around 0.5 to 0.75 all the time. And this illustrates one of the problems with just using the template system on its own with no other signal processing. So what's happening here is like the template, because it's just a bunch of uniform constant numbers, that is very close to what just random noise looks like, because the Fourier transform of random noise over time will have a consistent uniform statistical distribution across the entire spectrum. And then, the correlation of that, random uniform distribution with just flat constant tends to be really high. So that is one of the things we get around with the smoothing and stuff that we do on the Pied Piper project, which is mostly what I'm going to talk about today. I should hopefully have opened this recently enough. Yes. Okay. So, okay, today I've managed to find a room that should hopefully be more peaceful than the last few places I was at, so I can actually say things and draw things on whiteboards, and it should be okay. Drag everything over to the closer one. Okay. So it sounds like the project, there's several different projects going on. You guys are you're doing the sound like visualization project, right?
We're doing sound and then mapping it to vibrations, but there is another team that's part of this that's going to watch the recordings. I think that is doing the visualization. Oh yeah, Vishnu's in here.
Okay. So, and then that visualization, so the types of features you're looking for, are they going to be like recordings of do you have actual well-defined example? Okay. So, okay. For doing that, so do you have like a bunch of well-defined examples of what what LED outputs you would have for what features would be present in the sound? Like, do you have recordings and things for what kinds of features you want to recognize, or do you have like some other? Okay. So in that case, if you are, I'm just making sure that. Okay. So yeah, actually, let's talk about that more. So if you, it sounds like you might not be able to use the. Okay. So in that case, so you're not going to have like well-defined, consistent templates for all of the different things you're trying to recognize, right? Because the thing about this template method that I've been leaning into for feature recognition is that you can use it to recognize multiple things present in a signal at the same time. And that sounds like something that you guys would be doing. And it would just be a matter of having multiple different templates and testing. Okay. All right, good. Okay, so yeah, so the template. Okay, real time. Yes, that's one of the things I'm going to talk about today. Because one of the way that we do things real time on Pied Piper is we have to use the, I don't know if you were here for when I started talking about this, but today I'm going to be talking about our interrupt timer system that we use for sampling audio while we process it. despite, not having a real multiprocess, like just having a single core processor. And also I'm going to talk about the signal processing that we use to make everything just to smooth over the smaller details in the incoming audio to make it so that it doesn't mess with the template method as much. So so this is the full Pied Piper code. Most of this isn't even to do with signal processing. Most of this is to do with like commanding random peripheral components to do things like take photos and do complicated file IO and things. But the main actual parts that we care about, here we are. So just as a quick review, the interrupt timer, which gets initialized somewhere in here. There it is. So the interrupt timer, all it does is we pass it a pointer to a function, and we pass it a number of microseconds that we want it to wait between calling that function. And the function we point it to is a function that records so we have a volatile input sample buffer, which it's just an array, in this case, of shorts, because our project is really heavily constrained by memory, so we have to store all of our audio samples as shorts rather than ints or floats. So for your guys' project, for doing stuff in real time, you'll have a volatile input buffer for your audio samples of whatever data type makes sense for you guys. You guys should hopefully have a higher resolution ADC, which would let you get better resolution than you can fit in a short. But obviously, if it's not any better than 2 to the 6, if you have, what resolution is your guys' ADC? Because obviously the main thing is that are you guys going to be super memory constrained with the size of your samples and how many you have to hold in memory at a given time? Okay. In that case, you can probably just get away with making your life easier and storing all of your frequency data as floats and using actual integers for your input sample buffer. So you shouldn't have to worry about a bunch of the annoying stuff we've been dealing with on this project. Anyways, the first thing you want to do is just make a buffer, just a volatile buffer that's the size of one of your Fourier windows. So what happens is the interrupt timer, every single, however many microseconds between samples it is for your sampling frequency it passes, it will call a function which will first check if the input sample buffer is full. And if it isn't full, it will write to the current location in it. The current, you will read an audio sample and write to the current location in it, and then move the pointer over. And then that pointer also has to be declared volatile. So, whoops. So this stuff, it has to all be declared volatile because in order for the compiler to not break and try to simplify things that can't actually be simplified, you have to declare these as volatile so that the compiler doesn't assume that these variables don't change when you're in the main loop and the main loop itself hasn't touched them. So that's why that all has to be volatile. Otherwise, you might get weird behavior where samples won't actually record, and probably some other bigger problems emerging from that. So you'll need input buffer and a pointer in it. And when that pointer gets to the end of the buffer, so the interrupt timer is the thing loading the samples into the buffer all the time. And then in your main loop, you will want to be polling to see whether the buffer is full at any given time. So yeah, in this case, we just have this function input sample buffer full, which it just returns true if the number we're indexing the input sample buffer with is at the end of it. And then if it is full, we have, when it is full, that's when you do all of your actual signal processing. So the main most important thing is that your code is able to execute all of whatever signal processing it does in the amount of time that it takes to record one Fourier window. So this means that it's okay if your code takes longer than the amount of time it takes to record a single sample. And that will almost certainly be the case because the even on an ESP32, which is a lot faster than the Cortex M4s that we're using, even on that, you're not going to be able to do a Fourier transform fast enough to do it within a single sample. Theoretically, if you could execute all of your processing and FFTs and things in the time it takes to record a single sample, you wouldn't need the interrupt timer anymore, but that's probably not going to be the case. So yeah, you have an interrupt timer constantly recording. Okay. Okay. So the main thing is, if that shouldn't be too computationally expensive, but the main thing is, so as your sampling frequency increases, the size of your Fourier windows is also going to get bigger. And then Fourier transforms, they are pseudo-linear, so they will get slightly less efficient at larger and larger window sizes. So if you start running into problems where, okay, I think the first thing you should do is to just run some benchmarks on your ESP32. So just make a really simple program that all it does is it just records one Fourier window of audio and then times how many microseconds it takes to process the Fourier transform of that window. And then, so if you subtract out, calculate the number of microseconds it takes to record however many samples are in your Fourier window, and then subtract the amount of time it takes to calculate the Fourier transform of that, and then subtract the amount of time it takes to record each individual sample. And then that gives you the number of microseconds you have left over to do actual processing that isn't the Fourier transform. And so I don't remember off the top of my head how many microseconds it takes our M4 to do a Fourier transform, but I think it was something like 4,000 microseconds to do a Fourier transform. And then, hang on, I need to do some napkin math real quick. So we have a sampling frequency of 4.096 kilohertz. So yeah, with our sampling frequency, which is very slow, and our Fourier window size of 256 samples, we have 62,000 microseconds-ish to do all of our processing. So the Fourier transform itself takes about 4,000 of those microseconds, and then that leaves us with plenty of time to do all of our frequency smoothing and feature recognition and stuff. So the main thing is, before you just run out and assume that something is going to be a performance issue, just make sure you actually measure everything first to make sure that it's actually going to be a performance issue. So like the main most important thing right now, if you're concerned about whether you can do something in real time, is to just go run benchmarks. Figure out exactly how long it takes for your microcontroller to do a Fourier transform and how long it takes to execute your feature recognition and everything. And then just make sure that the combined amount of time that is less than the time it takes to record enough samples to do a Fourier transform. So even if you can just barely make the mark by like 100 microseconds or something ridiculously tiny, like just don't go. Yeah, just the main thing is make sure that you actually know something's a performance issue before you go optimizing it. Yeah, so in fact, I might, the programs that you would use for doing the benchmarks are really, they're really simple, and I might just, if I have time later this week, I might just post 1 or 2 programs that measure important things like the time to do a Fourier transform and the time to record a sample. Oh yeah, and that's the other thing. So Arduino, one of the very annoying problems with Arduino programming is that the time that it takes to record a sample when you use the built-in analog read command tends to be ridiculously way longer than it needs to be. So when we call our analog read function on our controller, I think it takes something like 200 or 300 microseconds to record, yeah, or no, sorry, that was an order of magnitude off. It takes 20 to 30 microseconds to record a single audio sample. And that is way longer than it needs to be. So this is something that I didn't look very far into because it ultimately wound up not being, like the performance wasn't that much of a problem, but there are ways that you can do where you can directly go in and mess around with the registers in the controller's ADC to get it to sample way, way faster. And you can actually set up a DMA buffer where rather than have the interrupt timer going off, you have a hardware timer built into the ADC that does all of the sampling, but like does the sampling itself in parallel with the code, like in parallel with the main program, and moves it into a buffer. And that can be, it basically just eliminates the actual time spent taking samples from your code, and it can free up a lot more performance. But going in and doing all of that, it requires that you get very intimately familiar with the actual, like with your actual hardware. And it introduces a lot of complexity and development time just because you will be digging through the data sheet for your processor on your controller. And then it's not going to be portable between different kinds of controllers. So I would recommend avoiding doing that if you can. But if you have to, like if the time it takes to record a sample is just way too long and it takes up too much time, then that is an option. But especially, yeah, I'm not that familiar with ESP32s, and I don't know if you would, yeah, I don't know how well implemented the built-in analog read command on ESP32s is. So on our M4, it takes 20 to 30 microseconds, which isn't great, but is doable for our project. If it takes something like 100 microseconds on your ESP32, and you're trying to sample it like CD quality audio at 40 kilohertz, it's just not going to work, and you'll have to do some DMA thing. But yeah, that's not something that I would know how to do. Like, you can find guides on the internet on how to set something like that up. It's not something I'm personally familiar with because we were fortunate with this project to be able to scrape by without it. But in general, it's like the DMA thing, it's like the interrupt timer, except even more painful to implement. So definitely avoid it if you can. But yeah, anyway, so continuing on with like how, yeah. So yeah, continuing on with like the interrupt timer implementation, the main thing is that so the main loop is just constantly polling to see if the input sample buffer is full. And then oh, that wasn't actually the code. There it is. And then the instant that it is full, the immediate first thing that has to happen before you do any other stuff is pull all of the samples back out of it. Because then that will make sure that you can keep recording more samples with no blind time. So the way that we do that in here is we don't bother setting every element of the input sample buffer back to 0. We just set the as soon as we pull all of the sample data out of it, we just set the pointer in it for the index. There it is. So we just set this thing back to 0 so that when we call the sampling function again, it can just start loading to the first position again. And then after that, we read all of the samples into the vReal array immediately. And then as soon as we set that pointer back to 0, we start doing the Fourier transform. And then from there, everything proceeds as if there's nothing weird and scary going on with an interrupt timer for our signal processing, at least. So yeah, that's like the main moral of the story with the interrupt timer is just make sure that you can actually do all of the processing fast enough and the time it takes for it to fill up its little volatile input buffer. And if you can, it should, everything should just work out fine as long as you are sure to like definitely declare everything volatile and make sure that you clear the buffer the instant it fills up. Because otherwise, like if I just did something as simple as put this line right here, this would prevent us from doing this in real time, because these 4 lines in our Fourier transform stuff is taking about 400 microseconds. 4,000 microseconds. And our interrupt timer is set to fire off and record a sample every 200 something microseconds. So just having the line where I set the sample buffer to 0 happening after these 4 lines and not before would completely ruin the ability to do real-time processing. So just make sure you set that, get all of the data out and set the pointer back to 0 absolutely as soon as you can. And I think the example code that yes. So yes, I actually just copy pasted a lot of the same code and changed some variable names between the PyPiper project and the example code I shared last week. So yeah, there shouldn't really be much more to doing stuff in real time other than the messing around with the interrupt timer. But that's only as long as you don't need to resort to the DMA thing, because once again, so on our microcontroller, it takes usually, I can't remember what the exact number was. I think it was 24 microseconds to record a sample. So the code will just, when it's inside of the function that the interrupt timer fires off, it will just sit here on this analog read command for some number of microseconds. And then that will, that gets taken out of your time budget for doing your processing as well. Yeah, so when you, if you just take the if you just have some like time budget, like your sampling frequency, or sorry, 1 million microseconds per second divided by your sampling frequency, minus the microseconds taken to do a Fourier transform, minus the microseconds required to record a sample times the number of samples in a Fourier window is your time budget to do all of your processing. And weirdly in our case, the analog read, like just the time spent recording the samples themselves, actually exceeds the time we spend doing Fourier transforms. And like I said, that's just due to the fact that the analog read, like the built-in analog read function, is very hit or miss as to how well it's implemented on different boards, where there are some boards where it takes literally thousands of microseconds to execute this command. So yeah, that's the main thing to look out for, is like how fast does this go? Anyway, so yeah, now I'm gonna transition back to I'm gonna close this so that my computer stops screaming. I'm gonna transition back to the Pied Piper code to talk about our smoothing that we do, because it actually helps the templates just work better in general, because you just remove a lot of the finer details that in the signal that can vary between different examples of it. And it also lets you reject things like random noise, which is what was causing the thing I was showing you earlier with the correlation to hover at an alarmingly high value all the time. So in general, most of the features that it sounds like you guys are looking for, it sounds like they're going to have well-defined frequencies. So the spectrograms of those signals, they will have, like the features you're looking for will have very sharp, well-defined peaks in their Fourier transforms that should hopefully be sustained over some meaningful number of time. It should hopefully show up in adjacent Fourier windows in your signal at least a couple times. And for that reason, so if you were looking for features that had really diffuse, like poorly defined frequencies, like if you were looking at something that is literally a noise distribution, then the processing we're doing on Pied Piper would be very, very bad, because the entire point of it is to eliminate that stuff. But in general, if the features you're looking for are, if they have sharp, well-defined frequencies in them that are like maybe not the entire feature, but they are just each feature has some characteristic sharp, well-defined frequencies in it, then you can do a bunch of smoothing to eliminate all of the other like noisier stuff that can vary from window to window to make the templates work a lot better. So I should be able to show an example. So what I'm about to show you guys is oh, that was the wrong one. So this is audio recorded by the Pied Piper traps. Specifically, I'm just going to show you guys spectrograms from them. So this is an example of what a spectrogram of like more or less random noise would look like. So on Pied Piper, we're a lot more concerned about not missing, like we don't care about our false positive rate very much. We just want to have like an absolute we just need to absolutely minimize our false negative rate as much as possible. So in our like positive detections of the audio that we have, there's a lot of, like most of them are just random noise that happens to have features that are reminiscent of the mating call buried somewhere inside of them. And you might, like the first, hang on, I want to find a good example of like what, I probably should have picked one out before this, but in general, if you just look at the raw audio stream from a microphone, just in mostly silent conditions, and you look at the spectrogram of that, it's going to look something like this. And especially if you have some kind of automatic gain control on your audio input, which actually, yeah, that's actually a really important thing to note. Do you guys know very much about your like microphone preamplifiers? So like, do you know if you have some kind of automatic gain control going on? Okay. So yeah, like, do you know if it's doing like, okay, so is there any kind of automatic? Oh, okay. So you know that your audio signal is going to be like linear, like the signal level, like you just have some linear gain in your audio feed all the time that's fixed. Because if you do, okay, so yeah, then if you do, that means that you shouldn't have to deal with a lot of the problems that we've been dealing with on this project, where if you have automatic gain control that tries to keep a constant signal level, it can actually cause problems for feature recognition because your microphone preamplifier will tend to amplify random noise a lot. So if that's not a problem for you guys, then yeah, so you shouldn't need to worry about a lot of the stuff that we're doing with subtracting noise backgrounds out of signals. But still the smoothing we're doing can still help with, it can still help with making the templates work better. So the smoothing we're doing, all we do is, rather than, if we look back at the, yeah, that should be fine, but as long as, the main thing is that you actually know what the absolute signal level is at any given time. Oh yeah, the smoothing. So the smoothing is something that that's separate from the gain control. So the smoothing is part of how we deal with the automatic gain control, like introducing some artifacts into our signal. But it will also just help with the template methods that I've been talking about so far. So automatic gain control in the mic, it makes it so that the main problem with it is that it makes it so that your signal isn't actually linear anymore with respect to the composition of what's inside of it. So like, I think this whiteboard marker is good. So if you have some signal as a function of time, and maybe if I turn off the lights, it'll be, is that better or worse? That's worse. Oh, well. Maybe this one's better. That's I think that's okay. All right, I'll just have to try to like. Can you see this okay? I don't know if I can see if I can. It's yeah, this is like leaned up against a window. I'll just put a chair against it and hold it. Okay, so if I just put it down here, it should be out of the glare. Okay, that should be good enough. So automatic gain control can cause problems for signal processing because let's say you have some signal as a function of time that looks something like this. And then let's say somewhere in here, there's some other signal that also shows up in the input feed. So let's say you have, for example, this consistent sine wave-ish thing over time at a relatively constant signal level. In here, there's suddenly a really, really loud noise that has a really, really big amplitude, and it is on top of the original signal. So this is ideally what you would want to actually see in your, oh dear, in your audio feed when you're doing your signal processing. Like the main thing that you want to be true is that your signal obeys superposition. If there is suddenly another signal showing up in the feed, the results that you see should just be the original signal plus the thing that's there now. What automatic gain control does that causes problems is that it will constantly adjust the gain of the input signal to maintain a constant-ish, like it will adjust the gain to maintain a constant signal level. So that means this signal, which is what you would want to see, would actually look something like this, where I'm going to draw the signal level first that the automatic gain control is trying to measure. You would see something like that instead. So that means if you were doing some feature recognition on this original sine wave thing, the feature in the original signal would be exactly what you were looking for. But the feature in this signal now, because the gain has gone down and it has been quashed to maintain a constant signal level, the feature that was once like perfectly as you would expect it to be now looks something like this. Because when that like transient thing shows up in the middle of it, what that means is the amplitude of the thing you were looking for has to go down. And then if you were looking for this in your audio feed, and then you're doing the template recognition with something that, with like if you're doing the template of this against this signal, you would get a very big number that would suggest that this signal has that in it. And if you were doing this template against this signal, you would not get as large of a number because the actual feature you're looking for has been squished in the middle here. So this is why automatic gain control can cause problems. It's because it makes it so that it just makes it so your signal isn't linear anymore. So if you add more and more signals together in your input, then the actual result you get isn't just the flat sum of all those things you put into it. So then the template method gets a lot less effective. And it just gets a lot more prone to interference. So as long as that's not a thing that you're dealing with that's happening, like if you know that you don't have any dynamic automatic gain control happening, you shouldn't need to worry about this. But if you, So yeah, if you add a noise gate, that shouldn't cause any problems. So that would just, yeah, that would just make it so that if your signal level was really, really small to begin with, it sets it so that it is exactly 0 all the time. And that as long as you know that the feature levels, the features that you're looking for aren't almost as small as your noise gate, then it's, yeah, a noise gate wouldn't cause any problems. Yeah. So yeah, the templating stuff. Yeah, so the other thing, I don't know if I mentioned this yet, but something that's really important to do when you set up your templates is to make them exactly the size, like the time of the template should be exactly the size of the signal, and it should have no margins of silence or anything on either side. And then you wouldn't even need to do anything explicit to account for silence. So yeah, that's why automatic gain control. Yeah. Okay, so yeah, this is why automatic gain control is it causes very bad, scary things to happen when you try to do feature recognition. But that should hopefully just serve, like, the moral of the story is don't have automatic gain control. Or if you do have automatic gain control, make sure you're doing it with some audio DSP that can actually tell you what the real signal level is at any given time. Otherwise, it just completely messes, like, so yeah, the smoothing, okay. I might not have enough time to talk about this, like the implementation of this fully, but in general, adding at least a little bit of time and frequency smoothing to your input, like in your signal processing before you do anything else with the signal. In general, that's going to be a good thing because it makes it so that transient, like really, really transient features that vary from just one Fourier window to the next in your signal will be eliminated. And that's a good thing because those types of features generally aren't going to be consistent with each other when you're trying to recognize. So say, for example, if you have some, if you're looking for a feature that's something along the lines of like some air, I forget what they're called. What do you call an instrument that has air running through it and that's how it makes a noise? Yeah, okay. Yeah, something like that. If you say you're looking for something that came from something like that, the sound, like the spectrogram of something like that, would actually look like it would look like a noise distribution, because, like, okay, for example, whoa. So the Fourier transform of something like that, it would be a lot, it would have a lot of transient bits in it, and it would be really, really chaotic. So So like that's what one Fourier transform of one time Fourier window would look like in audio from something like that. Another one would be sort of similar, but again, it would just be all over the place again, and then again and again and again. And that's because things that come from like the technical thing that's going on is the instrument is generating through some like it is essentially generating an infinite spectrum of noise, and then the rest of the instrument is filtering that noise and through like a resonance chamber. But the end result of that is over time, unlike something like a pure tone, the distribution, like the frequencies coming from that instrument are going to have a distribution, like a smooth distribution, rather than really, really well-defined spikes and things. So if you average together a bunch of time windows, you would get something like that, where that would be different from a lot of other sources of noise that have like most audio signals you see that have well-defined frequencies just have one gigantic consistent spike like that. So it's important to add a little bit of time smoothing to your input just so that if you're trying to recognize features that have a really smooth statistical distribution over time, they'll actually be recognizable. Because otherwise you're trying to use a template that was recorded with like some recording that had that was of a random statistical distribution of something. And then if you do the dot product thing of that template with your incoming audio, where say your incoming audio has that feature in it, but it's just different, like it's just different numbers that have been chosen out of the same statistical distribution. The template won't work very well because that was for like one specific roll of the dice. And then in order to get around that, you need to add a little bit of time smoothing of the frequencies that you're recording. So just average together a few Fourier windows using, okay, you could probably get away with just a rectangular moving average, but I would recommend a Gaussian one if you can. Just so that it's like consistent, just so that you are able to see things that have a statistical distribution over time rather than just very well-defined, consistent frequency peaks over time. So yeah, hopefully by next time I should have, so by next time I'll try to get the original example code with like some of the smoothing and stuff going on in it, so that I can hopefully demonstrate how it improves feature recognition. Because like the main thing that it'll get rid of is the thing that I showed at the start, where the correlation coefficient of random noise in the room was very high for just a constant number across the entire template. So yeah, that's all I really have time to talk about today. I have class in a couple minutes. Are there any quick questions? Okay. Okay. In that case, if there are no questions, I'll see you guys later.